So let's say we have some object. And it's spinning. And let's say this is some three-dimensional object. It's spinning around some axis. So this axis of rotation, basically a linear pivot point. And we've got it spinning in this direction. So spinning, I guess that would be counterclockwise when viewed from above. Or alternatively, how could we attach a single direction, like an actual arrow, to that rotation? If it's spinning like this, how would you describe the direction of its angular velocity?
Sorry, did you say it was spinning counterclockwise?
Counterclockwise when viewed from above, yeah. So spinning like this. How would you describe that rotation as a single direction? Yeah, we could use the right hand rule, right? If it's spinning like this, you can curl the fingers of your right hand in the direction it's rotating, and your thumb tells you the direction of the angular velocity. So the angular velocity is an upwards vector here, usually written as omega is the angular velocity, or sometimes called the rotational velocity. Its magnitude would be measured in degrees per second or radians per second, because we're just describing how fast it's rotating. But angular velocity needs a direction also. It is a vector because the direction something is rotating matters. For example, if you have something that's spinning like this, that's one kind of rotation. Its rotational velocity would be this way. But if I tilt it, so it's now spinning like this, now its angular velocity is upwards. Those count as different angular velocities. Even if it's spinning at the same speed, direction matters there. So angular velocity does have a direction. And if we want to establish an idea like momentum, like for instance, translational momentum, how do we typically define translational momentum?
Mass times velocity.
Yeah, mass times the translational velocity, v. And you can think of that as a combination of how fast the object is moving, including direction of travel, times a measure of, well, how would you describe mass? What does mass of an object mean?
It's like the resistance to changing its motion.
Yeah, the more massive an object is, that just means it's more difficult to change the motion. It's how much it resists and attempts to change its velocity. And this can also be seen in the equation force equals mass times acceleration. If you want an object to accelerate, you've got to apply a force to it. But the more massive it is, the more force is needed to make it accelerate at a certain rate. So it's very useful to think of mass as a measure of difficulty, how difficult it is to change the velocity of an object. So momentum is ultimately just a measure of how fast the object is moving, including direction of travel, multiplied by how difficult it is to change that motion. And rotational motion can be, or rotational momentum can be defined in almost exactly the same way. Rotational momentum usually written as a capital L, which does count as a vector. It's also going to be a measure of how the object is spinning instead of moving through space. So omega, the angular velocity. So a measure of how fast it's spinning, including direction of spin, that is the axis it's rotating around, multiplied by a measure of how difficult it is to change the spin. But that's not just mass there. What is it going to be?
It's going to be a moment of inertia.
Yeah, this is what we call the moment of inertia, the capital I. moment of inertia, or sometimes just called inertia. But the idea is moment of inertia is serving the same role in this definition that mass served in the translational momentum definition. That mass is a measure of how difficult it is to change the translational velocity of the object. Likewise, moment of inertia is a property of the object that tells you how difficult it is to change the angular velocity. A large moment of inertia means it's difficult to make the object change how it's spinning. A small moment of inertia means it's very easy to change the spin. So for example, with this spinner here, if I want to make this start spinning, it's very easy to make it start spinning. If I want to change the axis it's rotating around, I feel a little bit of pushback when I try to tilt it like this, but it's fairly easy. Or if I want to make it stop, slow down, also very easy. So this has a fairly small moment of inertia. But if I had something that was, let's say, a bicycle wheel, it would be more difficult to get it spinning in the first place. If I tilted it around its axis, that would be even more difficult to change the moment or change the rotation. If I wanted to bring it to a stop, it would be more difficult. So what's the difference there? How is the bicycle wheel different from this little spinner that makes it more difficult to change how it's rotating? What differences? Yeah, the mass is part of it. The bicycle wheel is much more massive than this little spinner. So generally, the more massive an object is, the more difficult it's going to be to change the rotation. Likewise, if we take that bicycle wheel and let's say we fill up the interior of the tire with cement instead of air, that's much more massive. So it's going to be much more difficult to get it spinning. And once it is spinning, it's going to be much more difficult to tilt back and forth. However, mass is not the only thing that matters. Because if I take two objects that are, let's say, the same mass, what else is going to make a difference in how difficult it is to get it rotating or to change its rotation once it's already rotating?
Is it like the distribution of the mass relative to like the axis of rotation?
Yeah, exactly. How the mass is distributed relative to that axis. For instance, with this spinner, if I attach some extra weights to it, let's say I take some heavy magnets and stick them around the outside, that's going to be more difficult to spin, and I'm going to feel more resistance when I try to swivel it. But if I take those same magnets and move them closer to the center, it's still going to be more difficult than it would be without the magnets, but it's going to be easier than it would be if the magnets were further out. So more mass means a larger moment of inertia, more difficulty, but also that mass being further from the pivot point, further from the axis of rotation, also makes it more difficult, whereas the mass being closer is going to be less difficult. So moment of inertia is not only mass, it's mass and distribution, how the mass is distributed throughout the object. In particular, further from the pivot point, further from that axis of rotation means more difficulty. And we can also see this to some extent using the units of measurement. For example, if we go back to moment of angular velocity, what is angular velocity measured in? What units of measurement would you use for that? Like if you wanted to describe how fast something is spinning, what units of measurement would you use to describe the rate of spin?
We use RPM.
You could do rotations per minute, but it turns out that the mathematics ends up being a lot more complicated if you're using rotations per minute. What units of measurement would make that a lot easier to use in the equations? What's a more natural measurement of how far something has rotated? Yeah, we usually use radians per second. So any angle, any amount of rotation can be measured in number of rotations or fractions of a rotation. Like you could say this is 1/4 of a rotation as a right angle. So you could define a right angle to be 1/4 of a full rotation. Or you could split the rotation into 360 pieces and label it in degrees. But there's nothing really natural about the number 360 either. There's nothing special about 1/360th of a rotation. It's just a convenient number to work with. But radians are a much more natural unit of measurement. 1 radian actually means something. Specifically, in any circle, if you have an angle that's exactly 1 radian, a 1 radian angle is defined as the amount of angle that makes the arc length the same as the radius itself. That's actually how radian is defined. 1 radian of angle measure means the angle such that the arc length cut off from the circle is exactly the same as the radius of the circle. Or if an angle is 2 radians, that means it cuts off an arc length that's twice as much as the radius. Or if the angle is 1/3 of a radian, that means the arc length is 1/3 of the radius, and so on. So radian measure is actually a direct comparison of the arc length versus the radius in that circle. And for this reason, because radian measure is such a natural geometric definition of an angle, radians tend to be the unit of measurement that works best in equations. Any equations from geometry, if you're using radian measure for the angle, the equations tend to be very simplistic. But if you use degrees, then there's almost always an extra times 180 over pi or times pi over 180 to balance that out. So let's say we're measuring the angle in radians. And then since we're talking about how much the angle changes as time passes, that's going to be radians per second. But radians is technically unitless. Radian measure, an angle measured in radians is defined as the arc length divided by the radius. Arc length would be measured in meters. Radius would also be measured in meters. So meters over meters cancel out. Radians is technically unitless. So when we say radians per second, we really mean mathematically just 1/seconds. We still usually read it as radians per second to make it more clear what we're talking about. But formally, the units of measurement of radians is no units at all. So angular velocity is measured in 1/seconds. Any questions on that so far? And do you happen to know what units of measurement angular momentum has? Or do you have any other equations that angular momentum is relates to anything else? For example, what would you have to do to change the rate of spin? If you have something that's spinning and you want to change how fast it's spinning, what would you have to do to it?
You would have to apply like a torque.
Yeah, if you apply a torque to the object, you can change its angular velocity. Much in the same way that if you apply a force to an object, you can change its translational velocity. And the equations for that are the exact same setup as well. If you apply a torque to an object, you cause a rotational acceleration or angular acceleration. And we can set these up in the exact same way we set up force and translational acceleration. Force applied equals level of difficulty, that is mass, times translational acceleration. Similarly, torque is equal to the rotational level of difficulty, the moment of inertia, times the rotational acceleration. And since rotation has a direction, as given by the right-hand rule, angular acceleration has a direction, and therefore so does torque. So the torque is the rotational push, the rotational effort you apply to make the object change its rotational velocity. And we can fill in units here as well. We know angular velocity is measured in radians per second, or 1/seconds. So what would be the units of measurement for angular acceleration? In terms of how does that relate to angular velocity?
Would it just be 1/seconds squared?
Yeah, 1/seconds squared. Because angular acceleration is the rate of change of angular velocity, change in angular velocity over change in time. Angular velocity is already radians per second. Then we're dividing by time, so that's an extra seconds in the denominator. We get radians per second squared. So angular acceleration is going to be in radians per second squared. which we should be thinking of mathematically as 1/second squared. Again, we would typically read it as radians per second squared, but mathematically it's just a unitless 1/second squared. And what about torque? How do you usually calculate the amount of torque that something is applying? Or how do we usually define torque? At least for the magnitude. Like if you're pushing on something and you want to calculate how much torque does that count as? Force is measured in newtons, but how do you turn it, if you know how much force is being applied, how do you calculate how much torque it counts as?
It would be force times the moment arm.
Yeah, force times the moment arm, the radius, and also times sine of the angle between them, but sine theta is going to be unitless anyway. If you take a look at the units of these though, force is definitely measured in newtons. What's the radius going to be measured in?
Meters.
Right. So that means torque is measured in Newton meters, which also technically could be written as joules, but we usually don't because we don't want to get this mixed up with energy. Torque is not an energy, it's something completely different. It just happens to have the same units. But if we write torque as newtons times meters, and also what is newtons? What does newtons break down to if you split it up into its most basic units?
Isn't it kilograms meters squared seconds squared?
Without the squared on the meters though. With meters squared, it would be joules. But we can actually see that going back to the original formula here, force equals mass times acceleration. What's acceleration measured in?
Meters per second squared.
Right. Acceleration is meters per second squared. And mass, as usual, is in kilograms. So if we define force as being measured in newtons, Newton has to equal kilograms times meters per second squared. So this is what a Newton is. Newton can be broken down into kilograms times meters per second squared. So torque is kilogram meters per second squared. That's from newtons. But then we also have an extra times meters from multiplying by distance. So overall, we get kilogram meters squared per second squared. Which means if we want the units on both sides of the equation to match up here, what does this have to be to make the units match up?
A kilogram meter squared.
Yeah, moment of inertia has to be measured in kilogram meters squared for this to even work at all. So that's the units of measurement for moment of inertia. It's always going to be measured in kilograms times meters squared, which suggests it is a mass times a distance squared. And that also gives us the units for angular momentum or rotational momentum. If we combine these, we get kilogram meters squared per second. And you could also think of that as kilogram meters squared radians per second. It's just that once again, radians is unitless, so it's not actually listed in the mathematics. Any questions on the units of measurement there so far? So let's take a look at how to calculate moment of inertia then. If moment of inertia has to be measured in kilograms times meters squared, this has to be kilograms times meters squared. That suggests we've got a mass times a distance squared, or an area, but area doesn't really make much sense in this context. So if we think of meters squared as some distance squared, if you're talking about a rotating object, what's the only distance that really matters there? What's the most important distance associated with some sort of rotation?
The distance from or to the pivot point.
Yeah, the distance between that piece of mass and the pivot point. In other words, the moment arm or radius vector. So we could write that as r squared. So we've got the mass of the object, and then r is the moment arm, the distance from the pivot point or axis. Axis of rotation. So this is the, I guess you might say, the most basic or most foundational way of calculating a moment of inertia. If you know the mass of the object and you know how far the object is from the pivot point, you can just multiply that mass times that distance squared. Any questions on that so far?
I have a quick question.
Mm-hmm.
So there was another equation that came up for the magnitude of angular momentum,
Mm-hmm.
and it was L is R times momentum times sine theta.
Mm-hmm.
But I was really confused as to how that equation was like
This
derived.
shows up, that one shows up specifically if you're talking about an object moving around, if you're talking about an object in motion, like you know it's translational momentum, and you want to write that also as a angular momentum as well.
So it's just converting the linear momentum to angular by choosing like a reference rotation point.
And the
Okay.
reason that works, let's say you have an object that's moving translationally. Let's say you've got some object in motion. So let's say an object of mass m that's moving with some translational velocity v. Presumably kilograms and meters per second. So you can calculate the translational momentum just by multiplying mass times translational velocity. But also, if you define a location to be called the pivot point, like let's say this location here is defined as a pivot point. You could think of this object as moving, at least temporarily, along a circular path. So if we have a radius vector here, radius in the sense of distance from the pivot point out to the object in question, you could think of that object as if it's moving along a circular path. And maybe it really is moving along a circular path. Maybe we're talking about circular motion here. Or alternatively, maybe this is moving in a straight line, but at that brief period of time, you can treat it as moving along a tangent line to that circle. So for a very short period of time, even if it's moving in a straight line, for a short period of time, you can treat it as being a portion of this circle. And if it's moving along this circular path or a portion of this circular path, that also counts as rotation. Because if you look at from a little bit before this time to a little bit after this time, if you trace out a radius vector at the instant a little bit earlier and a radius vector a little bit later, there is a change in angle as time passes. And again, this is true even if the object is moving in a straight line. Even if the object is moving in a straight line instead of a curved path, as the object moves, the radius changes its angle. So there is an angular velocity, even if the object is moving in a straight line. Any questions on that so far?
No, that makes more sense. No.
And if we want to compare the translational momentum versus the angular momentum, I times omega, moment of inertia times angular velocity. For a moment of inertia, we can just multiply the mass of the object times how far it is from the pivot point squared. So I is just m times r squared. But what about omega? How would we determine how fast the angle is changing?
Is that based on the linear momentum?
Well, once we establish a relationship there, we can set up a description of how translational momentum and angular momentum are related. But to relate translational velocity to angular velocity, we're going to need to go back to some geometry first. If we go back to that circle in the first place, the way angular momentum is defined, or sorry, the way angle is defined even more foundational than angular momentum. If you've got a circle and you have some angle located at the center, remember what I was saying about radian measure earlier. Radian measure is defined in terms of the ratio between the radius, so let's call that R, and the arc length. Arc length being the distance along the circle, but just within that enclosed region. And let's call that S for now. S is usually what's used for arc length. So if we know the radius and we know the arc length, the angle is defined in terms of those values. Let's say we call this angle theta. The whole point of radian measure is that we define the angle as the ratio of arc length versus radius. Arc length divided by radius. So like I mentioned earlier, if we say that the radian measure of some angle is, let's say, 1/3, radian measure of an angle being 1/3 just means that the arc length is 1/3 of the radius. Or if we say that the radian measure of an angle is pi/4, that just means that the arc length is pi/4 times the radius. We really are just talking about the arc length as some fraction or multiple of the radius. This also means you can solve for arc length as just radian measure of the angle times the radius. So this is what I was saying earlier about the idea that if you're using radian measure, then the geometric formulas become very simple. The distance along the circumference of the circle in this region is just the angle, if you're using radian measure, times the radius. If you're using degrees instead, you'd need an extra times pi over 180 to get it to balance out. But in radian measure, the formula really is this simple. And if we want to convert this into a formula for velocity, S is a measure of distance. How do you turn distance into velocity?
You would divide by the time it took to travel the distance.
Exactly. If we just divide both sides by time, and formally we should attach a delta to these also. That tells us that change in position over change in time, that is translational velocity, equals change in angle over change in time times the radius. And what do we call change in angle over change in time?
Angular velocity.
Yeah, change in angle over change in time is the definition of angular velocity. The omega we've been talking about, in radians per second. And then we still have times radius here. So this relates the translational velocity and the angular velocity. If you know the translational velocity, like how fast you're moving along the circumference of the circle or even along a tangent line, that angular velocity is equal to the translational velocity is equal to the rotational velocity, how fast you're spinning, times the radius of the circle. And we can use that as a substitution. You can replace translational velocity with angular velocity times radius, or vice versa. You could replace angular velocity with translational velocity divided by radius. And notice that this gets the units to work out right also. Translational velocity is meters per second. We divide by meters, we're left with 1/seconds, or radians per second in the text. So if we make that substitution, if we replace angular velocity with translational velocity divided by radius, what happens when we combine these?
We would get MV times R, and then MV is just momentum.
Exactly.
Momentum times R.
Right. So that means that in general, you can make that conversion. Or not in general in terms of always, but just if you've got an object that's moving along a circular path or along a line tangent to that circular path, you can say that the angular velocity is equal to the translational velocity, the angular momentum is the translational momentum times the radius. That is how far it is from the pivot point. And note that we're just talking about magnitude here. This does not take direction into account at all. In fact, the translational momentum is the direction of motion. The rotational momentum would be given by the right-hand rule. So that would be in the outwards direction here. So this does not take into account direction. This is just talking about the magnitude. This is also assuming that the object is moving along a tangent line. That is, the object is moving in a direction perpendicular to the radius. If it's moving in some other direction, you also need a times, I think was it times sine theta, did you say?
Yeah.
Where theta is the angle between the translational velocity and the radius. So that's basically to take into account, like if this is traveling in some other direction, if it's traveling in some other direction, the sine theta basically just finds what component of it is perpendicular to the radius. But theta in this context would be the angle between the translational velocity vector and the radius vector itself. And the sine theta accounts for just the perpendicular component. So generally you can use this as long as you're talking about an object that's moving in either a straight line or a curved path, but you can treat it as a tangent line. And you're talking about the angular momentum relative to some pivot point. You can use this to make that conversion. Translational momentum magnitude times the radius, how far the object is from the pivot point, times sine of the angle between the radius and the velocity vector. That tells you the magnitude of the angular momentum. That is, this object, even though it's traveling in a straight line, technically has an angular momentum. And this is one way to calculate it. Any other questions on that?
So if we had absolutely like no reference pivot point, then we couldn't use this.
Mm-hmm. Yeah,
Okay.
this whole thing is based on the idea of having some point that we're calling the pivot point, some reference point to measure from.
Okay.
If you're just talking about an object that's moving through space and you haven't defined a pivot point, then it doesn't really make sense to talk about angular momentum. All of this rotational stuff is always defined in terms of some pivot point. Even if you just got an object in floating in space that's tumbling around itself, you would just treat the center of mass as the pivot point. But if you don't have some sort of way of defining a pivot point, none of the angular stuff works anyway.
Okay.
Any other questions on that so far?
No.
And I think this idea particularly becomes relevant in a certain problem about a kid jumping onto a merry-go-round.
Yeah, that's where we dealt with that equation.
Yeah, in that case, even though the kid's running in a straight line, the kid is running and about to jump onto the merry-go-round. So what location would you treat as the pivot point for purposes of the kid's running?
It would be the center of the merry-go-round.
Yeah, because even though the kid is not actually rotating around anything yet, as soon as the kid jumps onto the merry-go-round and grabs on, then both the kid and merry-go-round are rotating around that one central pivot point, the axle of the merry-go-round. So even if something's not rotating yet, if you know it eventually will be rotating, then figure out what location will it be rotating around and use that as the pivot point for the whole time. Any other questions on that so far?
No.
All right, let's investigate moment of inertia in a little more detail then. This idea of mass times radius squared works really well if the object is just one tiny point that's some fixed distance from the pivot point. But that's not always the case though. You might have an object that's more spread out. So this formula works great for a point mass. A point mass, meaning all the mass of the object is concentrated at one single location. The usual classic example is something like if you've got a rock tied to a string and you're just spinning that rock on a string around your head. Then the rock is a certain tiny piece of mass, not tiny in the sense of very small mass, but tiny in the sense of not taking up very much space. And so all that mass is effectively one specific distance from the pivot point. And it doesn't really have to be absolutely small. It just has to be small compared to the radius distance. For instance, the Earth itself is huge, But if you're talking about it as orbiting around the sun, the Earth is fairly small compared to the distance between the sun and the Earth. So if you're talking about the orbit of a planet, you can treat the planet as a point mass because it's small compared to the orbital radius. However, if you've got something that's more spread out, like let's say this lumpy object that's spinning around some axis, you can't just use mr squared, because what radius would you use? You've got a mass, you could talk about the mass of the whole object, but where is that mass located? Can we choose one radius and say all the mass is at this distance from the pivot point?
No.
Not really, no, because the mass is like some of the mass is really close to the pivot point. Like this piece of mass right here is almost at the axis of rotation. This piece of mass is a little further away. This piece is further away still. This piece over here is very far from the axis of rotation. So each little bit of mass is a different distance from the pivot point. So what you could do is you could imagine splitting this up into little pieces. If we've got this axis of rotation and this object that's got all this mass spread out, you could say this piece of mass, or really this entire column of mass, you've got some column of mass that's all a certain distance from the axis of rotation. So you could take this little bit of mass times this distance squared, and then take the next column and say you've got this little bit of mass times this slightly larger distance squared, and this bit of mass times this slightly larger distance squared. You could split up the rock or whatever the object is into regions that are a certain distance away from the pivot point. For each one of those regions, take that tiny bit of mass times that distance squared. And then what could you do with all those little bits of m times r squared?
We can sum them together.
Yeah, we can just add those all up. So more generally, we would say that the moment of inertia is the summation of r squared times little bits of mass. R squared times, and we would usually call this dm. dm meaning a tiny piece of m, a little bit of mass. Although if we're adding those together, the thing is this still gets us just an approximation, because this piece of rock or whatever is not all exactly one distance. Like this edge is a little bit closer, this edge is a little bit further from the axis of rotation. So if we want to make this more and more accurate, what would we have to do? How can you make a summation of tiny pieces more accurate?
Wouldn't you just have to split the rock up into tinier and tinier pieces?
Yeah, we get a more accurate result, because really this is just an approximation. We get a more and more accurate result the more and more smaller and smaller pieces we use. If we split this up into very thin pieces, we get a more accurate result, because each one of those smaller pieces is a more narrow band of approximated radii, approximated distances. So if we make the pieces smaller and smaller and smaller, if we take the limit as dm, the tiny piece of mass approaches 0, what does a summation like this turn into if you take the limit as the pieces get smaller and smaller? Think back to calculus, where you've seen this idea before. If you're approximating something by adding together a bunch of little pieces, but you make the pieces smaller and smaller and smaller, how would we rewrite this summation using notation from calculus?
You could rewrite it as an integral.
Exactly. This turns into an integral. When we take the limit, when we make the more and more pieces smaller and smaller, instead of writing it as a summation, we'd write it as an integration. And instead of being an approximation, this is now exactly equal to. This is really all an integral represents. The integral really just means adding up a whole bunch of tiny pieces, but making the pieces smaller and smaller, taking the limit, so the approximation becomes exactly equal. So this is really the definition of moment of inertia. Moment of inertia can be calculated as establishing some pattern of tiny pieces and multiplying for each one, distance from the pivot point squared times the tiny piece, and then integrating over all the mass. Actually, applying that can be kind of complicated because you can't really integrate r with respect to m if those are different variables. So typically what we do instead is find some way of rewriting dm in terms of r, like split this up into little pieces, find a way to write the tiny bit of mass in terms of the tiny bit of distance. So instead of integrating r squared with respect to m, you're instead integrating r squared times some formula with respect to r. So it's going to look like integral of r squared times something with respect to r. And then you can integrate usually from the center out to the edge in terms of r values. So this always turns into some sort of definite integral, sometimes more complicated, sometimes fairly straightforward. But the thing is, you use an integral like this to create a formula, but ultimately formulas for any typical object have already been determined. We have formulas for a sphere rotating around its center, or a cylindrical rod spinning around its center, or a cylindrical rod spinning around its own edge, or a flat disk spinning in place. So any typical shape you would expect to see, there's probably already a formula for moment of inertia for that shape. And typically you would just look those up on a data table. Let me pull up one example here. So this, for example, would be some of these shapes. If you got a shape, you can just look up that shape on a data table like this, and it should tell you the formula for it. For example, a ring spinning around its own axis is just going to be mr squared. And in that case, you get the simple mr squared because all the mass of this hoop is one single distance from the pivot point. Or if you're talking about a solid sphere rotating around its own center, the moment of inertia is still a mass times a radius squared, but also with this fractional multiplier, 2/5 times mass times radius squared. Or if it's hollow, it ends up being 2/3 times mass times radius squared instead. So various different formulas depending on what shape you're talking about. In general, it's almost always going to be some fraction times a mass times a distance squared. But what exactly that fraction is depends on how the mass is distributed. And typically, the more the mass is distributed out towards the edge, the larger the moment of inertia is going to be. That is, the more difficult it is to change the spin. Any questions on that so far?
Wait, just to clarify, you said the more mass that's on the edge, the larger the moment of inertia is?
Right, because if we go back to the basic idea of mass times radius squared, even though it's really adding up a bunch of little pieces of mass times radius squared, mass being at a larger radius counts for more. In fact, since the radius is squared, larger radius counts for a lot more. Like if you've got a piece of mass that's some distance from the pivot point and another piece of mass at a distance, let's say 3 times as far away. If you're 3 times as far away, but then you're squaring it, what does that 3 turn into?
It'll be a 9.
Right. So if you have some piece of mass that's 3 times as far away versus some other piece of mass, that further piece of mass counts for 9 times as much because it's 3 times as far away, but then you square it. So larger distances count for a lot here because the radius is being squared. For example, if you have, let's say you've got a bicycle wheel of a certain mass and a certain radius, and let's assume all the mass is out at the edge, like you filled the tire with cement or something. That's a certain level of difficulty to spin it around. If you then expand the wheel, making it, let's say, twice the radius, but keep it the same mass. Twice the radius, but the same mass. You double the radius, but then you square it, so you get 4 times as much moment of inertia. So changes in radius get amplified by that squared. Any other questions on the moment of inertia stuff?
No.
All right, then looks like that's all the time we have for today. But feel free to contact me elsewhere if you have any other questions, and I will see you next time.
Thank you.
You're welcome.
Thank you.